part 6 video of synchronous motor, and today we will be discussing synchronous condenser. What is condenser? Condenser is old name of capacitor. And what is the advantage of synchronous motor? The synchronous motor will be working as unity power factor load, lagging load and leading load. Okay, so the condenser, it is the capacitor, and the synchronous condenser, the synchronous motor will be known as synchronous condenser because it is running at synchronous speed and it can act as condenser or capacitor. Okay, synchronous motor can act as condenser or capacitor and under some specified conditions. We will be seeing when the synchronous motor will be acting as synchronous condenser, that is, it will be acting as a capacitor. And how it is known as capacitor or synchronous condenser, it will be working as leading power factor load. The synchronous motor will be working as a leading power factor load, that is, the current will be leading. Also, under additional conditions, the synchronous motor will be working as UPF load and lagging load also. The same synchronous motor will be working as UPF, lagging and leading load. Okay, it is interesting, is it? So before discussing details, we'll be having some assumptions so that the constant load is applied to the synchronous motor, and we'll be supplying the constant frequency, and the field excitation current of the synchronous motor will be varied. Before going to the synchronous motor, let us see what is happening when a coil is supplied with a AC. This is a AC source and we are going to give current to an inductor or coil. When switch I is closed, what will happen? It has to take a current of I, and this is the inductor, and when alternating current is there, it will be setting up a flux. Okay, so let us say it is setting up a flux of phi. And how the current can be calculated in this condition, how much it will be? It is depending on some back EMF. Here, when the current is flowing, this will be creating a voltage across this inductor. We can say it is back EMF. Is it? So the current will be depending on the difference of voltage, that is circuit voltage, which will be V minus EB by impedance. Here impedance, it can be simply XL or square root of R square plus XL square. Anyway, we are interested more in this particular item. V minus EB will be the circuit voltage here. Okay, so this is concerned with a single coil supplied with AC voltage. Now let us see, we are having one more coil which is independent. One more coil and it is supplied only with DC, and also there will be flux. So the two cases, one is coil supplied with AC here and another coil which is entirely independent and supplied with DC. Again there will be flux. If both the things are bring together, what will happen? Actually we know there will be a effective magnetic field. The flux lines will not cut each other, we know, and if flux 1 is there and additional flux is there, and if both the coils are brought together, what will happen? It will be creating a effective flux like this. So it will be creating a effective flux. Okay, so previously we have discussed how the current it will be. It is V minus EB by Z, and now we can consider that this is similar to our rotor magnetic field in a synchronous motor, or the DC field winding in the synchronous motor. And what about this one? This is a phase winding of a armature, that is stator winding. This is happening in synchronous motor. Okay, so there will be a resultant voltage, that is EB. We can say If only this coil is there, we can call it as EB. Now, because of this additional flux, it may create a resultant voltage, and that will be the vector sum of voltage and back EMF. Let us see detailedly what is happening. Only thing you remember that we are having a rotor field winding here which is DC, and armature or stator winding which is AC supplied, and obviously in synchronous motor both will be nearer. And EB, the back EMF, will be now controlled by DC excitation. By varying the excitation, what happens? By varying the excitation, the flux will be controlled, and by controlling the flux, the total flux in the area can be controlled. By controlling the flux, we can control the back EMF. Now, we are going to discuss about synchronous motor itself. We are having a constant load. Already we have seen the condition. Now we are telling about a constant load, and let us say there is a constant load line here. It is a constant load line, and let us say constant load line means the synchronous speed. It is running at synchronous speed n, and the stator voltage, that is the applied voltage available here like this. So 0 to V, that is the applied voltage to the stator of synchronous motor. Then the back EMF. Back EMF will be having a opposition to applied voltage as we know, and it is shown like this EB1, back EMF 1. Okay, and how the angle it is here? It is the load angle. It is the load angle. As we increase the load, we know that there will be a load angle as we discussed in the previous video. This is the load angle. So here the constant load is assumed, and obviously this angle alpha will be same for every condition. Now what happens? So this is the voltage V and this is the EB1. Together it will be making the vector addition of V and EB1 as the resultant voltage. Resultant voltage, what it is doing? It is controlling the current being taken by the machine. The synchronous motor current will be decided by the back EMF and voltage vector addition, that is resultant voltage here, ER. So we can say the load current, it is like this. The resultant voltage will be deciding the load current or the current taken by the synchronous motor. So this is the applied voltage V, and there will be a back EMF, and back EMF we know it is controlled by the excitation is not shown here, and based on the V and back EMF we will be getting what? Resultant voltage, and the resultant voltage will be deciding the current here. And you can see a interesting thing here. It is theta. What is theta? It is the angle between the resultant voltage and the load current. It will be almost equal to 90 degree, and it will be always like this. Why? Because the windings in the synchronous machine, we are assuming that it is highly inductive. Because of highly inductive nature, it will be having lagging current, and when it is highly inductive it will be 90 degrees. So this 90 degree will be almost 90 degree in almost all cases. Now what is the next step? We will be seeing the load power factor angle. The synchronous motor will be supplying or getting a voltage V, and it is taking a load current I. So this is the supplied voltage and load current. The angle between voltage and current, we know that power factor angle, that is phi here. Okay, under this condition what we can understand? This is what type of load? Voltage is here and the current is lagging. So we can definitely say this is a lagging power factor condition. So this current is lagging behind the applied voltage. Okay, and this is a particular excitation, and this excitation is generally happening when the exciting current is less than the rated current. At what condition? The excitation current will be lesser than the rated excitation of the synchronous machine. So that will be known as under excited synchronous motor. There will be a rated excitation for every synchronous motor, and below that excitation we'll be telling it as under excited, and the under excited synchronous motor is lagging power factor load. Now we'll be considering unity power factor condition at a particular time. In this condition, what happens? The voltage V is available still, and the difference is the excitation will be increased. The DC field excitation is increased, and by increasing the excitation, the back EMF also will be increased like this. Okay, so by increasing the excitation to the rated value, we'll be increasing the back EMF, and what happens? The resultant voltage becomes like this. And we know the current taken by the machine will be lagging by 90 degrees, and that will be known as I2. I2 here, it is the load current taken by the synchronous motor, and it is lagging behind the resultant voltage by 9 degrees in theta angle as discussed earlier. And the current I2 is now in phase with V. What does it mean? That is a unity power factor load. That means by increasing the excitation from under excitation to the rated excitation, we can control the power factor of synchronous motor to unity power factor. The current is becoming in phase with the voltage. How? By just increasing the excitation current to the rated value and making the voltage current in phase. So now the synchronous motor, we can say it is running at what power factor? Unity power factor. And this is known as normal excitation. It is just that it is having the rated current of the synchronous machine. Normally excited synchronous machine will be acting as what type of load? Unity power factor load. Now this is our $1,000,000 answer for the leading power factor load or synchronous condenser load. Condenser takes leading current. What happens here? Let us see. There will be a supply voltage similarly previously discussed, and the constant load is available, and we are increasing the excitation current further. When the excitation is increased further, back EMF increases. And when the back EMF increases, what happens? The resultant voltage become like this. Okay, vector addition of V is like this, back EMF is increasing, and obviously this will be the resultant voltage. We are mentioning it as ER3 here, resultant voltage. And we know the current taken by the machine, that is I3, will always be 90 degree like this, 90 degree. The reason we told, it is a highly inductive winding. So this 90 degree angle, it is all everywhere, it is the same. And the I3, it is coming like this. You can say the difference of I3 here, and the voltage is here, and current is leading to the applied voltage. Effectively, the machine is taking what? A leading current, or the machine is becoming a leading power factor load now. So what happened? We have controlled the excitation, and this is the over excited condition. Overexcited synchronous motor is working as leading power factor load. This condition will be known as what? Synchronous condenser. Why? Condenser, it will be taking, or capacitor, it will be taking a leading current. Here the synchronous motor is becoming a leading power factor load, and it is known as what? A synchronous condenser. So to summarize, let us see the power factor lagging, it is available, unity power factor is available, leading power factor is available only just by changing the excitation. Under excited synchronous motor will be becoming lagging power factor load. Rated excited synchronous motor will be working as unity power factor load, and over excited synchronous motor will be working as leading power factor load. And this particular session, that is our topic, synchronous condenser, and it is the wide industrial application of synchronous machine or synchronous motor. The motor can be working as a capacitor, so this can be used to improve the power factor of bigger factories or bigger transmission lines. So this is the overexcited synchronous motor working as leading power factor load. Now many trainees have asked doubt how the EB can be higher than V. So if the one voltage is increased, it will be not taking a current. Why it is like this? Can you answer? Actually, it is due to the magnetizing effect of the field. With the field and with the armature winding together only, effectively the voltage it is increasing. It is not just the EB increasing. As if we can see, if you are putting some deposit into the bank, then only you will be getting some interest, is it not? So cumulatively only the total increasing. Like this, our synchronous machine also.